Hello, welcome back. So we're going to continue our discussion for chapter 16 about binary search tree. Okay. And in this section, we're going to take a quick look of Java collections. So how the binary search tree is defined in Java collections. Okay. So Java collections framework, it supports tree-based data structure. And there are two tree based data structure, the tree set and the tree map. Okay. And we're going to, in this chapter, we're going to take a look at the tree set. And the set, if you recall, the data structure is about unique item, no duplicate items in the data structure. Okay. So So that's also, if you recall, binary search tree also doesn't allow duplication. Okay, for Java collections, tree set, and the tree set, if you take a look at the Java collections framework, the hierarchy, okay, and the tree set in the hierarchy, we can see it's implement the tree, the set interface, also implement the sorted set and the navigable set. So it implement the those interfaces, okay? And if you recall, Java collection itself also has also support the operations for add item, search item, and delete items, okay? So the tree set, it implements those interface. And we have an example in this chapter and demonstrate how we are going to use the tree set. And the last section in this chapter is about the application of binary tree and structure. It's about Huffman coding and encoding. Okay, so Huffman tree. So what is that, the concept? So let's take a look. Okay, so Huffman encoding and Huffman coding in the we have like ASCII code. So in ASCII code, the character, the char is 8 bits. Okay, yeah. So Huffman coding is another scheme. Okay, so it's kind of a compression scheme. And for ASCII, each character is 8 bits. Okay, no matter it's frequently used or not. Okay, but in Huffman coding, the scheme is code. It's variable length, so not fixed. Okay, and also binary. So same thing like ASCII code is also binary. The difference is this is variable length. So it uses variable length binary code to represent characters. Okay, binary, that means 0 or 1. Okay, and so the idea is if the character occur frequently, then they are assigned shorter codes. Yeah, because you see, the goal is to compression, is it? So yeah, if it appears very frequently, we then use shorter codes. So then you can compress. The compression can be achieved better, while less frequent character can be assigned longer codes. So that's the idea. And also it follow another rule. It's called immediately decodable. So the immediately decodable, the idea is no character's code is a prefix of another character's code. So keep that in mind. So one character's code cannot be a prefix of another character's code. So that's the Huffman coding. And with this definition, then let's see how do we do it. So here gives us some idea. Okay, so you have, like suppose you have a paragraph or article that has a lot of characters, and you can count the frequency, is it, and give the frequency weight. So here, suppose for some thing, we have this 5 character, and we give the frequency rate. Okay, weight. So this is the frequency weight. P is 10 percentage, F is 10 percentage. We can see E is the most frequent one. Okay, so the weight is higher, larger. Okay, so this is a frequency. And here it gave us some codes, the binary code. But if you take a close look, you will find 0 for E is the prefix of R. Is it? So this violates the rule of immediate decodable. Okay. And also if we take a look at this 100 is also the prefix of P, is it? So it violates. So this is not Huffman. So not Huffman coding. Okay. So then with this frequency table, how do we build the Huffman codes? Is it for these 5 letters? The question is. Okay, so here is the algorithm to do the Huffman encoding. Okay, so the precondition that we needed to know is a list of character and their weights. Okay, so basic weight probability that will occur. And then we sort them in ascending order by the weights. Okay, then we can build a double tree. We call it bottom up from the weights. So here it's not top down, it's bottom up. Okay, we call it a double tree. We will see what does that mean. Okay, so we are going to combine the 2 smallest one into a subtree with their sum as a root and the weights as a left and the right child. So 0 0.1 is equal to 0 0.1, and then sum them to 0 0.2. Okay, so this is P, suppose this is F something, is it? So you are going to, so this is bottom up, okay? And repeat for all weights of the combined. Then here maybe you have 0 0.15 is S, okay? And then you can sum them. So this is 0 0.35. So keep doing this, okay? So and 0 0.2 and then 0 0.35. So E, okay, R suppose. So you keep doing this, okay? So that's how the tree is built. Okay, built. And once you have the tree, then you can find the code. Because for all the left, we assign 0. For all the right, we assign 1. Okay. Then from the root all the way to the leaf, you have the path. Then you can output. Is it like for P? Then maybe it's all 0. Okay, for F, then it's 0, 0, 0, 0, 1. Okay, something like this. Okay. Okay, so that's the idea for double tree for Huffman encoding. So how do you assign the binary code to each character? So we needed to build this double tree with the character's frequency. Okay. So here it gave us the idea, like I just showed, is it? So with P and F, is it? And then you sum them up. So this is a sum of 0 0.1, 0 0.1, is it? And then you come to K, okay? So here it's 0 0.2 plus 0 0.2. You get 0 0.5. Okay, then come to R. Okay, R is okay. So here you have this 0 0.4 plus that 0 0.25. So we come 0 0.65. And then we have this 0 0.35. That's okay. So 0 0.35 plus this 0.65, you come to 1.0, okay? So we don't have anything that, and the root is supposed to be 1.0, 100 percentage, okay? And then for each of the character, you just follow the tree path. Is it okay? And this is P. Is it all the left branch using zero to represent? So that's how P comes with 0, 0, 0, 0. Same thing for F. It's 0, 0, 0, and 1. Is it? That's how it comes. And K, that's 0, 0, and 1. Okay. And R is 0, 1, and E is 1. Okay. And for this, you can clearly see it follows the immediate decodable, as it no code is a prefix of the other code. So it doesn't meet that condition. Okay. So this is called Huffman coding. Okay. And it's variable length. Yeah, because of variable length, then it can do the compression. It will help a lot for compression. Okay, and then next, let's see. Okay, that's kind of we do encoding. Is there, if you, so generally speaking, a lot of time you do encoding and the echo part is the decoding. Is it suppose you have some codes, is it, and then 0, 0, 1, and then 1, and then 0, 0, 0, 1. Suppose you have this, this is what you received. How do you recover? So are those characters? Is it? So how do we do that? Okay, so that's called decoding. Okay, so you're reading list of character and their Hoffman code. So here, same thing. We first need to build the character tree. Okay, build a character tree is top down. Okay, and and then we from the list, 0 left, 1 right, okay, and fill data with asterisk until the leaf node we fill with a character, okay. So if you recall previously, P is 0, 0, 0, F is 0, 0, 0, Y is it something, and the E is 1, is it? So the idea is you go with star and follow this is 0, and then star, then 0, and then star. Is that you fill with, and also go 0 and star go with 0. But then we have it. And then this is that P. P is at the leaf node. Okay, same thing 0, 0, and here you go to F. Okay, this is 1. Okay. And I remember there we have uh, maybe R or S, something that maybe here is that R, and here is that E. If it is, this is 1, 1, 1. So you have the list of carrier and their code, okay, like this. And then you build this tree. This is tree is called character tree. Okay, we build the tree and then we can, so here is a message, some secret message. Is it with this secret message, then we can decode. Okay, so okay, 1, okay, we start with rule. Okay, then we know it's E. That, and then you read 0, 0, 0, 0. Okay, you read 4, 0, 5. Oh, that's P. Okay, and then you have 0, 0, 1. Oh, that's S. Okay, 0, 0, and you follow, you reach the leaf node. Okay, that's that. Then you read, okay, that's 0, 0, 0, and 1. That's it. And you reach F. That's it. So you can decode the message. Okay, so that's the whole idea about Hoffman encoding and decoding. Okay. So this is mostly used for compression. It's not used for security. Okay, so here, like what I just explained, is it so you once you build this character tree, is it when you have this secret message, is that you just follow this character tree, Hoffman tree for decoding, is it? So one started root, okay, then you reach this, so you know, okay, this is E. And then you can go ahead, okay, 0 and 1, you reach this. So that means it's R, okay. You just keep following. Is it okay? Next it's 0, 0, 0, and 0. Okay, 0, 0, 0, 0. Okay. We reach P, okay. So that's P, okay. And then you just follow 0, and then 0, and then y, you get to k. Is it okay? You get to k. Oh, oh, this should be k. Okay. So that's how we then do the decode. Okay, recover it back. So basically, you compress it once you receive the compression the code, then you can recover it back. Okay. Okay, so that's about the application. So we can see why we put it in the binary search tree chapter. You can clearly see it's also a binary tree. It only has two uh, uh, child nodes, either left or right. Okay, and if you recall the two photos about the national park, so they came from Squirrel National Park. Okay, it's a beautiful national park. Okay, so that's the information for this chapter. In our next lecture, we are going to go over the coding examples. See you.